let's talk about SMA as an actuator material and what's good with it and bad with it, and also from a MEMS perspective. Well, what is good with it is first the material itself. It's as I said, very typically it's a titanium nickel alloy. There's also other materials, but the titanium nickel has the largest shape memory effect of all known shape memory materials at the moment. The main advantage is that it's really the actuator with the highest known energy density. That means that if you need to make a small actuator that needs to perform a very, very high work output, you should use SMA. There's also cost. It comes at a cost. For one, there is a limitation to the amount of cycles you can go from the how many cycles you can do before it starts losing, before it starts forgetting its memory state. And that amount of cycles, that depends a lot in how much you deform the material. So the deformation, if the strain of the material is, say, 10%, local strain is 10% or more, you're going to be rather limited to maybe a few hundred of cycles only. Whereas if the strain is very small, say a percentage, you can easily go to hundreds of thousands, maybe 1 million different cycles. But so the strain of the material, the amount of deformation will determine how many cycles you can go with it. Another disadvantage is that the phase transition depends on we say it's deep. If you go above the martensitic transformation, it's austenitic, and below it's martensitic. But this exact phase transition temperature depends on the local temperature, of course, but also on the effective stress in the material. So if the material is stressed, that point will shift slightly. It will also depend on the exact material composition. So titanium nickel is typically almost a 50-50 percentage mixing of titanium and nickel. If you go from 50-50 to, say, 50.05 over 49.95, then your conversion temperature can easily change already for 10 degrees Celsius. So these materials are in practice very difficult to exactly predict because in manufacturing you'll have some kind of variation from batch to batch. So basically what people do is that you make a batch, and then after you make the batch you actually measure the temperature and say, oh well, now I have a material of this transformation. Whereas it's very difficult to on forehand exactly determine, very, very precisely where that's going to be. Another limitation for use as an actuator is that it rather behaves as an on-off material. I mean, hot is going to be memory, cold is going to be deformed. It's very difficult to have keep a temperature somewhere in between, where it's like, it's going to be stayed in between. It is possible, but it's very difficult to control that, because your temperature conversion goes very fast. It's only, maybe 3-4 degrees Celsius going from one state entirely to the other state, and in between you have some kind of in-between stresses that will shift that transformation temperature and so on. So it's going to be difficult. So it's an on-off actuator, really. It's going to be difficult to use it for gradual control of a motion or a force. And there are, as we're going to see in the next slide, there are quite some challenges when you want to integrate it with MEMS. It's not a standard CMOS material. It's not a silicon or a spray-on material. It's difficult to integrate. And that's what this slide is showing. So to integrate into MEMS, there's basically two different strategies you can use. The first is an in situ deposition, where you sputter it on. But you're going to build in stress in that material, and therefore it's going to not act as an optimal material. It's going to be shape memory, but it's going to be not as good as you want it, not as good as if you would make a bulk material. Another way of getting around that is to say, well, I'm going to make thin or small bulk materials and then integrate them. Once I make them, they're going to have the optimal material properties, and then I'm going to integrate them into my microsystem. And there's several strategies to do that. At KTH during the past 10 years, my group has focused a lot on specifically doing that. And this integration we do either with adhesive bonding or using eutectic bonding, or using what we also done is using SMA wires, and then use a wire bonder. And so instead of using a wire bonding for contacting chips, as you're going to see in the lab, we're going to, instead of using little gold wires for contacting MEMS structures electrically, we're going to put an SMA wire in the wire bonder and really use the wire bonder to integrate wires onto the MEMS. I'm not going to go in detail of how this is done. So there's ways of integrating the material, but they're typically not standard, rather expensive, and or very specialized to do that. The structuring of the material, because you may want it to have a certain, you typically want to have it to a certain shape, so that means you'll have to structure it. And one way to do that would be etching or machining it, like milling it or drilling it, and each of those methods is rather difficult. For one, it's a very hard material. Titanium oxide is a very hard material, and nickel is very hard, to machine. And also, it's also difficult to etch. You're going to need very, very harsh etchants to do that, and it's going to be anisotropic, and it's not going to, it's not easy. Then you're forced to build in this reset spring system. Otherwise, you're not going to have, you're not going to deform your material. So you'll have to think of that when designing a material. And finally, to have it work, you'll need to supply heat. And there's two ways to do that. There's a direct current heating or an indirect heating. Direct current heating is that you send an electrical current to the SMA, and you use the resistive heating of the material itself to give the heat. That seems easy, but there's a specific problem with that. For one, it's a very conductive material, so you'll need a very high current to create the heating. So it's going to be power. You're going to need a lot of power to do that. And secondly, just to electrically contact titanium nickel is difficult, because the titanium forms an extremely stable oxide immediately when it's in air. So you'll need to get rid of that oxide before you bond a contact wire to it, and that's not going to be easy, and it's not a standard process either. So that's troublesome. Indirect heating means that basically you integrate a heater structure on or near to the structure, the SMA itself, and so you use the heat of the heater to indirectly heat the SMA. This is my last slide on SMA. This is if you want to know more about SMA. I can recommend the thesis of Henry Gardin, made in my team. It's from 2012. You can download it just on KTH, and here you see the web address. And the introductory section is maybe 50 pages. If you want to read, he really describes, how to use SMA in MEMS, and he shows the progress that we've made in this field during the past, say, 10 years. Another very good book is one by Manfred Kohl. Manfred Kohl works in Karlsruhe. He wrote the book Shape Memory Microactuators. We worked together extensively. Manfred Kohl, he's really Mr. Shape Memory in microsystem world, I would say. And so this book will give you a very good overview. You can also try to look in Wikipedia, read a bit more, or find some review article here. But this review article is 2004, tells you a little bit more about thin film integration and how to do that. Okay.